King es profesor de Ingeniería Química de la Universidad de Purdue. Tiene experiencias en altos cargos ejecutivos en el gobierno y en la industria. En el 2004 fue director fundador de los programas Ciberinfraestructura de la Fundación Nacional de Ciencia y vicepresidente de Investigación y Desarrollo en Eli Lilly y Warner Lambert. El Dr. King comenzó su carrera como miembro de la facultad en la Universidad de Wisconsin, donde se dedicó a los métodos matemáticos y computacionales para la microhidrodinámica. El Dr. King es miembro de la Academia Nacional de Ingeniería y miembro del Instituto Estadounidense de Ingenieros Médicos y Biólogos. Durante su carrera investigativa ha sido ganador del premio Alan P. Holbrook del Instituto Americano de Ingenieros Químicos, el premio para las iniciativas en investigaciones de la Academia Nacional de Ciencia y un premio presidencial de investigador joven de la Fundación Nacional de Ciencia. Estamos muy agradecidos de tener al Dr. King. Thank you so much for coming here. Thank you for staying in our university. Thank you.
Thank you very much for the kind introduction. Yes, and it's a pleasure to have the opportunity to give two presentations. The main presentation is actually on Thursday, and it's about the role that universities play in bringing basic knowledge, creating basic knowledge, and applying that towards solving great societal challenges and economic problems and contributing to society. But today I am going to give a talk on fundamental research, basic research in fluid mechanics. Because of course I have both aspects in my career. In my own research in fluid mechanics, it's very basic fundamental research. Applications are many years, if ever, down the road. But then another part of me is working on very applied research directly with entrepreneurs and industry to try to take ideas from the university and in a relatively short period of time of 5 to 10 years, take them from the university laboratories to commercialization. So what I'm going to talk about today is basic research that was published just over 2 years ago in a chemical engineering journal called Industrial and Engineering Chemistry Research. It is a journal published by the American Chemical Society, and it's in a special issue honoring my colleague, Professor Ramkrishna. And this particular paper was selected for that month by the editors of the American Chemical Society to be the editor's choice. And one of the consequences of that honor is that the American Chemical Society allows unrestricted and free download of the research article, even for people, even for anyone, even those that do not have a subscription to the journal. And this is considered a contribution to the public good for one paper in every month in all the journals that they publish. And so if you're curious about my talk today and you want to see some more details, now of course at a university you usually have access to all the major journals. So if you log in through your university accounts, you should be able to access, this is one of the major journals in chemical engineering. So you should be able to access it. But even your friends who have no university connections, if they're curious, they can go on the internet and they can download this particular paper because it is an editor's choice free distribution. So I'm going to talk about the microhydrodynamics of ellipsoidal particles and a little bit about the history. And for those who are specialists in fluid mechanics, you know that when you try to look at particles that are non-spherical, ellipsoidal in shape, inevitably the mathematics involves elliptic integrals, the formulas get very complicated. So most people, unless they have to, don't want to look at ellipsoids. They like spheres. Spheres are much easier. But one of the points of this paper is that despite the obvious appearance of elliptic integrals, for some very important problems, there is a surprising simplification where the actual final answer has no elliptic integrals, despite your intuition. And that's basically the main story that I'm going to talk about today. But there is another underlying theme, and especially if you see both presentations today and Thursday, it talks about the fundamental tension, especially in American universities today, between creating knowledge, basic research, and the pressure from society to be useful and provide translational research and convert knowledge into economic impact. And more universities, including my university, Purdue, is challenged to have economic impact. Classically, universities were supposed to be about education and creating knowledge, and if you do those things very well, that was good enough. But today, that is not sufficient. The universities are also supposed to have economic impact. So the main presentation that I'm giving on Thursday will be the story of how we took a new idea coming out of the university and did more research around that idea the first few years, made some very important decisions to put additional resources and effort behind this great idea. And then the first step was to win a very competitive, and this is the headline from the newspaper. You see it's 2012. I will leave a copy of the slide so you can actually see the fine print. It's May 2012. This was the headline in the local newspaper about a $20 million award. In this case, it was the Department of Energy of the US government awarding my institute. I was the director of this institute. Because of the early results were so promising, we won this award to commercialize this new process. So that's 2012. The project actually started in 2010 with internal funds of the institute. And then in 2017, so 5 years later, the manufacturing plant, so this plant and the project by this point require $100 million. So from original 20 million, and before that, a few hundreds of thousands of dollars, that's how it started. But eventually, when you actually build a plant, it is, in 2017, the groundbreaking for this plant in Janesville, Wisconsin. It took about 7 years, and also 5 years after that $20 million award. And this is actually the Twitter of Paul Ryan, the Speaker of the U.S. House of Representatives, U.S. Congress. So this is Paul Ryan right here. This is Paul Ryan. And he is the representative in Congress for the city of Janesville. So that's why he was very proud to participate in the groundbreaking. And also he sent out the Twitter in, you can actually see here, 3rd of August, 2017. So it's all in the public record. Now, as I said, the university is basically now about two things: having economic impact and also having creating basic research and fundamental knowledge. Now, people like myself who are in administration in the university. So my main role at the university now is head of chemical engineering. So in addition to being a professor, I am responsible for the operation and growth and future of the School of Chemical Engineering at Purdue University. And one thing about administrators at universities is the faculty are very suspicious of it. Because once you are in administration and not as active in research and teaching, the faculty think of you as someone who has kind of gone to the dark side. and no longer to be trusted. So one of my core beliefs is that to be an effective administrator and to be an effective leader, you must always stay active in research. So you may notice that this particular paper and the work I'm going to talk about today is the other side of my life. It is how I stay connected with my faculty and with my colleagues, because when they see me doing this research, they know I can still be trusted, because I can still do mathematics, I can still do research. And in fact, if you look at that 2015 paper in Industrial and Engineering Chemistry, there are no co-authors, there are no grad students. I wrote the paper and did all the research completely by myself. Okay? So this is the other side. So what you're seeing today is one of the few times I can talk about my research. In fact, the research is so fundamental that the government will not even pay for it. Okay. So that is how pure the research is. And also, when you get to the end of the presentation, you probably conclude that you wouldn't want to pay for that research either. Now, not someone is willing to do it. But in some sense, that is one of the role of the university, is to create knowledge solely for the sake of creating knowledge. And so, when I die, I told my wife and my family, I want my basic research to be on my tombstone, not the translational research. So, of course, one of the most famous scientists, physicists, on his tombstone, this is Ludwig Boltzmann, and his famous equation from thermodynamics is on his tombstone, S equals K log W, the entropy equation. It's very famous. So I told my family, on my tombstone, this is the equation that I want. Of course, I'm not sure they're going to do it, but that's my request. So psi is equal to n dot x times phi. And only the experts in fluid mechanics in my special subfield of microdynamics will know what this means. This equation is not as famous as this equation, but still it is the equation that applied to me. And again, after my talk, I hope you will agree, and you can all write letters to my wife, please, Professor Kiss, put this equation. And the more people say it, the more she will believe that it's an important equation. Right now, she thinks it's just a crazy idea. Yeah, she is not a mathematician, so she doesn't understand that. Okay. So why is this so fundamental, and why is this important? And why did this story get selected as an editor's choice by the American Chemical Society? So in some sense, it's a very old problem. So as you know from your fluid mechanics class, every engineering student actually learns this, that in 1851, George Stokes, of course the professor at Cambridge University, solved the problem of a translating sphere in a viscous fluid. And that's 1851, 167 years ago. And today, every student, civil engineering, chemical engineering, mechanical engineering, physicists, chemists, biologists, they all learn Stokes' law, which is the hydrodynamic drag on a sphere undergoing a steady translation in a viscous fluid. Now, what's interesting is about 25 years later, so a quarter century, so back in the 1800s, things happened very slowly. So life was progressing very slowly. Today, if somebody finds a solution for a sphere, then the solution for the ellipsoid would appear the next day. Because we are working so fast today, and communication and the internet, everything happens very quickly. But in the 1800s, things are much more slowly, and so even though in current context, we could have solved the problem right away, but still it took a quarter century for Anton Overbeck. Not only was he a physicist, he's actually a physician. He discovered the way to solve and extend the solution of Stokes for translating ellipsoid. So you take a non-spherical shape, an ellipsoid, and you move it in a viscous fluid, and this is the paper that appeared in 1876. Now, of course, in addition to translation, you also want to look at rotation, spinning. And again, things happen very slowly. So the problem for the rotating ellipsoid was not published until 1892 by Edwards in a journal called Krell. And so these numbers are how many years ago? So 167 years ago, 142 years ago, and 126 years ago. Okay. Now, just to remind us what we're talking about here, if we go to a standard textbook that chemical engineers use, like Transport Phenomena, by Bird, Stewart, and Lightfoot, this is where I used to teach in Wisconsin. So this is a textbook that came from Wisconsin, and this is a photograph of a page from chapter 2 where they explain the creeping flow around a sphere, and they show the Stokes solution. Of course, it's a sphere, so it's in spherical coordinates. And here, from that same book, same chapter, is the velocity in radial and angular coordinates, the radial velocity and the angular velocity, and then the components of the stress tensor, the radial and the normal and shear stresses. Of course, you also have to solve for the pressure from the Stokes equation. And then when you integrate the pressure and the normal stresses, you get the normal force. You integrate the shear stresses over the surface of the sphere. You get so you get the form drag, and then you get the tangential component. And so when you add these two, of course this is buoyancy. If you add these two, you get the famous Stokes law that says that the drag, the force on the sphere, due to the hydrodynamic resistance, is the famous 6 pi times the viscosity times the radius of the sphere times the translational velocity, or the difference in the speed between the velocity and of the sphere and the fluid. Okay? Now, and of course, this is always also used in the context of sedimentation. So when we look at the coffee we drank this morning, how long does it take the coffee particles to settle? Well, the coffee particle is very small, so it'll take a long time to settle. So we use Stokes drag in many ways today. And of course, for the students, we don't want to confuse them, so we want to be very logical. So we teach them that when you solve spherical geometries, you first convert all the basic equation to spherical coordinates, solve everything in spherical coordinates. If you have rectangular geometry, then you use Cartesian coordinates. If you have cylindrical geometries, you use cylindrical coordinates, and that's the simplest story that we can tell. So for that reason, we actually do not tell our students a little secret, that if you take this result from spherical coordinates and you convert it back to Cartesian coordinates, you actually find a surprising simple results that we do not tell the students, because we don't want them to know that life has shortcuts. Okay? So here's the shortcut. If you take that force per unit area, so that's the surface traction, which in the notation of transport phenomena is the pressure at R minus the radial component, and here's the normal stresses, and then there's the tangential stresses, and then you combine them to calculate what is the actual force vector. And so here is the radial component, here's the angular component of force. But this combination is exactly the unit vector in the z direction. And the z direction is the direction of the uniform stream. So the final answer, if you want to convert it back to Cartesian coordinates, is that the surface traction, that is the force per area on the sphere that you integrate over the surface, is actually a constant vector in the z direction, with the constant equal to 3/2 mu v infinity over the radius r. So it is not a complicated directional dependence. So even though in spherical coordinates, you have these sine thetas and cosine thetas and so on. When you convert everything back to Cartesian coordinates, it's actually a very simple expression. And in fact, it's so simple that if you take that constant and integrate it over the surface of the sphere, the constant times the integral over the surface of the sphere is just like the constant vector times the surface area. The surface area of the sphere is 4 pi r squared. So that's how you get the 6 pi. So in fact, you don't even have to use spherical coordinates. If you were to use Cartesian coordinates and say that there is a constant uniform stream, v infinity, and the sphere itself is moving in some other direction with a vector velocity u, then the net difference is v infinity minus u. And the surface traction in just standard Cartesian coordinates is this constant vector, the difference between the fluid and the particle speed, times 3 times the viscosity divided by 2 times the radius. It is exactly that constant that when you multiply this constant by the surface area, 4 pi r squared, so here it is, 4 pi r squared times t, remember t is constant, you get slope-slop. Okay? Now the reason why we don't tell the students is because we don't want to confuse them. Well, why do you make us do all this work in spherical coordinates if the final answer is so simple in Cartesian coordinates? If you tell me the surface traction is a constant, of course I know it's equal to this, f over 4 pi r squared. It has to be. But of course, how do you prove that it's a constant other than doing all this work? Okay? So the important conclusion for the constant vector translational boundary condition, the surface traction is also a constant vector in the same direction. And what's even more surprising is if you now look at rigid body rotation of a sphere as the boundary condition. So a spinning sphere, the surface traction is also a rigid body rotation. Again, we never point this out. In fact, most instructors of fluid mechanics don't even know this. I talked to some of my famous colleagues who taught fluid mechanics for 20, 30, 40 years. And all these years, they never realized this thing. And again, the reason why they never realized it is we always look at the answer in spherical coordinates. We never look at it back in Cartesian coordinates. So in fact, here is the result. In chapter 3, the spinning sphere is also worked out in transport phenomena. We even assign it as homework for many of our students. And there is the velocity in the azimuthal direction. It is only a swirling motion v sub phi. And so the equations of change only have a phi component. And we solve that equation, we integrate it, and we get the angular velocity times the size times r to the minus 2 dk times sine theta. And then we show the students how to calculate the torque. And the torque is the famous 8 pi viscosity angular velocity times the radius q. Okay? And then we just leave it there. But if you actually went back and look at this, and look at that velocity field, you can actually show that the surface traction, if you go ahead and calculate the surface traction, is itself a rigid body rotation. And just like on the previous slide, if you convert everything back to Cartesian coordinates, again, normally you would have no reason for doing this, but if you now, because of what I tell you, you're curious and you go ahead and work this out, what you actually discover is that instead of spherical coordinates, if you say that there's an ambient vorticity that's constant, a spin in the motion, and relative to that spin in the fluid, the sphere is spinning this way. So the spins don't even have to be in the same direction. These can be two pseudo-vectors pointing in two different directions. The only thing that matters is the difference between those two rotations. And that cross the position vector x. So this is a vector now, position vector on the surface of the sphere, surface of the fluid. So this is Cartesian vector x, and then that divided times the radius of the sphere times the radial coordinate r to the third power. Now there's an r in here, so this is r to the minus 2 when you do this. This velocity field is the same Cartesian representation of the v sub phi, because the phi direction is the cross product. If this is in the z direction, then the cross product of this is a vector in the phi direction. So the two solutions are equivalent, but the Cartesian solution is the more general expression. And now if you work out the torque, if you work out the traction T, you find that it is actually equal to this cross product. And so finally here it is. So in terms of the torque, the same torque that you have there, the surface traction of the sphere is a rigid body rotation, just like the boundary condition, because this T cross X, this is rigid body rotation. And this is a constant, 3 times 8 pi radius of the sphere to the 4th power. And if I told you, just like on the other slide, in the other slide I said the surface traction is a constant when the sphere is undergoing constant translation. If I gave you that fact, you can just use Stokes' law to figure out what that constant has to be. So in the same way, if I tell you that the traction is a constant times the rigid body rotation that is linear and proportional to T, the torque, then you can figure out this relationship because, of course, it has to be consistent. If you take the cross product of the radial vector times the surface traction, this is the torque. So you go ahead and put this equation, you use the back cab rule, so this simplifies to this expression, and finally here it is. And so it is in fact, does give you the torque. Okay? And so over here, this expression, and the fact that this T has to be this, all of this can be calculated by this self-consistency condition. Because if the torque is a rigid body rotation, if the surface traction is a rigid body rotation, then the torque must have this constant so that the equation is self-consistent. So the main story again is if the boundary condition is rigid body rotation for a sphere, why is the traction also a rigid body rotation? Now, these results for the sphere were actually known when I wrote this book, Microhydrodynamics. So this book was written in 1987, 88, 89. It was published in 1991. So even, so 1988 would be exactly 30 years ago. So 30 years ago when I was writing this book, I already know the answer for the sphere. And it has to do with the integral representation theory. So some of the fundamental results for viscous flow, a velocity representation using a Green's function for the velocity field in terms of so-called single and double layer potential. So this G, script G, is the Green's function or Auxin tensor for Stokes' law. So here's the actual expression. And K is essentially the traction field of this Auxin. Sigma is the traction field of this Auxin tensor. So the velocity of a viscous fluid, disturbance generated by a particle, can be written as a superposition of single layer and double layer hydrodynamic potentials. This is exactly the same as electrostatics, where in the theory of electrostatics, you have the electric field of a charged conductor can be represented by a distribution of charges or single layers and a distribution of dipoles or double layers. Okay? And so one of the fundamental results of this is that the double layer operator K, the eigenvalues of the double layer operator, eigenfunctions of the double layer operator are in fact a rigid body boundary condition, and the adjoint of the double layer K star has as its eigenfunctions the eigenfunctions of the adjoint are the surface traction. Okay? So what happens in that original 1988 work was that I know that in the case of a sphere, if you look at the structure of the kernel, this dot product surface normal times x minus c, for a sphere, this dot product is this angle and this angle, and because for a sphere, you have an isosceles triangle, you have this famous result that n of c times x minus c is equal to n of x times c minus x. And when you have this identity, then this kernel for k becomes self-adjoint. So k is equal to k star. And because the operator is self-adjoint, the eigenfunctions have to be the same. So this t, for the rigid body motion, eigenfunction of K star is got to be the same as the eigenfunction VRBM of K, and the only thing that can be there is this constant. So the conclusion from the theory of integral representations for hydrodynamics is we actually understand, without going through all the mathematical calculations, we actually can prove in advance that this relationship has to be true. So now, of course, that this requirement, the fact that this is an isosceles triangle, is only true for a sphere. So if you go to any other particle shape, including an ellipsoid, a non-spherical ellipsoid, this relationship will not be true. So that is why, if you now look at the classical solution of Oberbeck and Edwards, you find that if you go through exactly the same steps to calculate the tractions on a translating ellipsoid or the tractions on a rotating ellipsoids, and this was done by Brenner in 1964, a very famous paper, you find the final answer can be written this way, that the traction for the ellipsoid is almost as simple as a sphere. It is equal to the force on the ellipsoid divided by 4 pi ABC, where A, B, and C are the semi-axes of the ellipsoid. But now there is a function n dot x, the dot product between the position on the surface of the ellipsoid and the local surface normal. And of course, as you go along the surface of the ellipsoid, n dot x is not a constant. So you do have a functional relationship between the traction and the constant vector. And similarly, in the case of the rigid body rotation for an ellipsoid, this is the Edwards solution, you discover, again, Brenner was the one to show this, you get a rigid body rotation. So you take the torque on the ellipsoid multiplied by this positive definite diagonal matrix, and then do a rigid body rotation of this new vector. And then again, it's a constant. This 4 pi ABC divided by 3 is the volume of the ellipsoid. And then P, then there again is the n dot x. Okay? Now, for a sphere, n dot x is just the radius of the sphere. So this result shows why for a sphere you get a constant. But of course, for an ellipsoid, it is not a constant, it is a function. But that actually raises another question. Even though this is showing that the relationship is not a constant, it is still a very simple function. So this raises the question. The surface traction is simply the dot product of n dot x times the boundary condition. So if it's rigid body rotation, it's rigid body rotation times n dot x. If it's a constant translation, it is n dot x times the constant translation. And notice also, and this is the point of the title, if the rigid body motion boundary condition uses force and torque as inputs rather than translational velocity and angular rotation, all the elliptic integrals are embedded in the expression for force and torque, so the actual expression for the traction, when expressed as functions of force and torque, have no elliptic integrals. It is simply geometric parameters A, B, C, and the position vector x. Very simple result. Okay. So the question is, why is the result so simple for an ellipsoid? Because of course, in 1964, when Professor Brenner calculated these answers, he had to take the original papers and their expressions for the velocity and calculate their velocity gradients and the rate of strain tensor to calculate the Newtonian constitutive equation for the deviatoric stress. And then you also have to calculate the pressure field. And then you combine the pressure and the stress to get the stress tensor. Then you take the complicated expression for the surface normal of an ellipsoid, and then you do the dot product. So it's a very, very lengthy calculation. And after all that work, everything simplifies to this. Okay? And so I actually have done this. So this is the 1964 paper by Howard Brenner, very famous paper. Chemical Engineering Science, 1964. The Stokes resistance of an arbitrary particle, arbitrary fields of full in one of those sections, section 7, he talks about the ellipsoid and takes these general ideas and applies them to the classical solution of the ellipsoid and calculates the surface traction. Okay? He skips out all the details, but if you patiently go through and redo his work, you find that it is a very lengthy algebraic calculations. Okay? And in fact, here, this is me. So to take the Oberbeck solution of 1876 for the velocity in the x, y, and z direction, and you take the velocity gradient in the x, y, so you calculate grad v. Then you calculate grad v transpose. Then you add in. Then you take the dot product with n. Then you also take the pressure field, which is also in the original paper, and you combine that with the surface normal, and combine all that together, and that gives you the vector t. So here's the calculation: 1, 2, 3, 4, 5. And at the very end, you do get. So in fact, this is also this is a very high resolution. So if you're curious, you can reproduce these pages and double check my calculations. And that's for the translation. If you want to do it for the rotation problem is a lot more effort. It takes about 10 pages of algebra to show the final answer. And Professor Brenner actually did this. I talked with him about this before he passed away. So and in his paper, he says it is a lot of work to do this. He doesn't give the details, but he was the one to do all this. Okay. So now the question is, can you go back to the theory of integral operators and understand why this happens? And by the way, I want to point out that I read this paper in 1978. And so this is when I first noticed this pattern. So for almost 40 years, I've been working on this problem. And that's the other thing about universities. In industry, you get 6 months to solve a problem. If you cannot solve it, you move on to something else because the survival of the company depends on economic performance. You cannot work on a problem for 40 years. So in a university setting, though, as one of your projects, if you feel passionate about something, you can work on it and keep working on it and working on it. And eventually, in 2015, I suddenly realized my mistake, what I was doing wrong, and I was able to find the answer. And that's what I'm going to talk about today. Is that what I remember is that if you want to calculate the adjoint of an integral operator, or any linear space, the definition of the adjoint is if you have an inner product between v and t, two different vectors in a vector space, then the definition of the adjoint is that k star is the one that produces the same inner product if you operate on the other element in the inner product, so k star on t, and then take the inner product with v, that gives you the same result as k acting on v inner product of t. So that is the definition of an adjoint. And in the case of finite linear spaces like matrix algebra, that simply gives you the transpose of a matrix. So the adjoint of a matrix is its transpose, but in the general theory of inner products, this is the formal definition of the adjoint. And so, of course, if you apply that to an integral operator, you take a vector field v and integrate over the surface with the kernel kij, and then you take the dot product with ti and integrate over the surface of the particle. That is the definition of the inner product, as well as the definition of the integral operator. And then you change the variables I and j and x and c, turn it backwards. Then you see this is equivalent to this expression v of k star when you write it out. So when you compare the two, you find that for integral operators on vectors, the definition of the adjoint, the kernel k star, is the kernel of k with the c and x switched, and the I and j transposed to j and I, just like in a matrix. So that is the definition of the adjoint in the case of hydrodynamics and integral operators and integral theory of hydrodynamics. Okay. Now, the thing I forgot, though, is that if you define a weighted inner product, so suppose instead of just the integral of the vectors v and t over the surface of the ellipsoid, surface of the particle, I now introduce a weight function w the weight function W should just be something that is positive definite over the entire surface of the particle. So if I now define a new inner product, and I remind myself that this is a weighted inner product by putting a W subscript at the bottom of the angular brackets, then what happened is if I now go through the same thing and figure out what is the adjoint, so here's the definition of the integral operation, and now there's the W from this inner product. Then I change the variables x and c and switch the labels I and j so I get this. So now this x becomes c, this x becomes c, this c becomes this x, and this x becomes the c, and so on. And now I compare that with the definition of the adjoint. So here's the same integral and the inner product. Now I compare the two, I see that the adjoint k star with respect to the weighted inner product is the transpose kji with the functional dependence of c and x switched. But now, because of the weight w, there's this extra factor here, wc times w of x, okay? So this is what I forgot for 40 years, almost 38 years I forgot that the adjoint depends, if you use weighting, it depends on this extra piece. Okay? And this is the very important piece that I forgot. Okay, so what does it mean? So now you go back to the ellipsoid. So there is a side view of the ellipsoid. And this is simple. We teach this in vector calculus, and we teach this in second year mathematics. That the surface of an ellipsoid, the surface normal at the point x is not in the same direction as the position vector as it would be for a sphere. In a sphere, the surface normal is always in the radial direction. But for the ellipsoid, they are not aligned. And the misalignment is given by n dot x times the local vector xi over ai squared. Okay? So for an ellipsoid, you have three, A1 is A, A2 is B, and A3 is C. So there's the index notation. Okay? So now if I go ahead and calculate this result for the kernel, for the specific case of the hyperdynamic potential, so I go and patiently work this out. So here is the kernel that appeared in the integral representation theory. And remember that famous n of x times c minus x. So for the sphere, I had a simple substitution of the isosceles triangle and the geometric identity. So I could replace this with the form that appears in the adjoint. But for the ellipsoid, I cannot do that. For the ellipsoid, I have to take this n of x and put in this result. So I did that. So here it is. Okay. Where n of x dot x is, of course, just 1 because of this final result. So this is the minus 1 that comes here. But now what I do is, if I want to have the adjoint, I don't want this. I want n of c dot c. So everywhere in the x, I want it to be c. That's what I want as the final result. So what I do is I take this n of x dot x, and I put it here, because this is the one I don't want. And the one that I introduced, I must put here. Okay? So that's why these two equations are the same. And remember, because I'm using a weighted inner product, I still get w of c and w of x. So now I realize that over here, this is now this. So just like a sphere, I've gone from this to this. But over here in this red box, I have something that does not happen for a sphere, only happens for an ellipsoid. But now here's the result. If I want this to be equal to 1, all I need is any, remember I didn't say what this weight function is. So now I realize if this weight function w of x is a constant times n dot x, then this and this will all cancel, and this will be equal to 1. So that's the answer. The index magic reveals that I get this final step here, kijw star is krj, if and only if the weight function is n of x dot x times some arbitrary constant. Okay. And now we understand why the simplification occurs. For the translating ellipsoid, the surface traction is a constant vector and linear with respect to f times the factor of n dot x. For the rotating ellipsoid, the surface traction is also a rigid body rotation and linear with respect to t times the factor of n dot x, and use the self-consistency of tractions, integrals over ellipsoid surface to yield force and torque, and then the divergence theorem to deduce the tensor of linearity. Okay? For example, in the case of number 2, Howard-Brenner's P matrix was in fact the inverse of the moment of inertia tensor, which again is a classical geometric result for an ellipsoid that is well known. And now we have the final result, which is, it is not just for the force and torque and the translation and rotation, which are the special cases in the eigenspace. For all eigenfunctions of the double layer operator, if phi is an eigenfunction of the k, and psi is the eigenfunction of n dot x, psi is the eigenfunction of k star, you have this result that psi has to equal n dot x times phi. So what are the implications? We now have a new approach to looking at geometries involving ellipsoidal particles. So again, these are of practical interest in suspensions because many suspensions are like rods or discs. They're not spherical in shape. So you now have a formal representation that says the velocity field can be the force produced by the particle, the torque produced by the particle. So these are the classical solutions of Vogelbeck and Edwards. And then everything else beyond that can be written as an integral of hydrodynamic dipoles with this unknown double layer density phi times the double layer operator. So this is a known existence of this velocity representation. And now we can write the double layer density phi as an eigenfunction expansion with unknown constants times the eigenfunction phi. And then when we solve the boundary condition for the particle, we can solve it for each eigenmode. So we can just take the inner product of the disturbance boundary condition, and using the orthogonality with respect to the weighted inner product, we can now say that that's equal to Cj times 1 plus lambda j. And if the eigenfunctions phi and phi with respect to the weighted inner product will be orthogonal. So just like in physical chemistry and quantum mechanics, we can apply the same type of mathematical representation. So in particular, the known boundary condition with this inner product, which are basically integrals over the surface of the ellipsoid, the constant Cj is 1 plus the eigenvalue dividing this boundary result. And so each of the Cj's can be determined once you have the eigenfunctions and the spectrum. So there's actually a new approach to solving very complex flow problems for Stokes flow of ellipsoidal particles. And just to illustrate that this identity holds, if we go to the 1926 paper by Jeffrey on the torque-free ellipsoid spinning in a linear field, we find exactly, of course, the eigenfunctions there also have to satisfy the general theory. So here, for example, in Jeffrey's paper, again in the modern interpretation, is the eigenfunction of k, and E dot n turns out to be an eigenfunction for k star, and sure enough, the two eigenfunctions are related by n dot c, and this here is just some constants. Okay. So of course, any specific solution that you have must satisfy the general theorem. Okay. And so here is a table from a conference presentation that I made. So if we go back to the Howard-Brenner 1964 paper, here are the eigenfunctions for k, for steady translation, steady rotation. Those are the eigenfunctions. And that's his equation 7.6 and 7.18. And here is the traction for k star. The eigenfunction for k star, again using that simple constants. And there's the n dot x. And here is the final result for Jeffrey. I did not talk about Jeffrey's 1926 paper, but in rheology and polymer rheology especially, that is a very important paper. And in the modern notation, we can say that the eigenfunction for the double layer operator k is n dot x inverse times s dot n, and the eigenfunction for the adjoint is n dot x cancels this, and you get just s dot n, the stress that times the surface normal times 1 over the volume of the particle, volume of the ellipsoid. So this is a very simple result of what is a very lengthy and messy expression in the original paper. So none of the expressions in the original literature are as simple as these final tables. But because of the general theory, we now have an immediate shortcut to a very simple understanding and expression for some of the most important physical quantities of these ellipsoidal particle models. And just as a reminder again, that the general result for all eigenfunctions of the ellipsoid is if phi of x is the eigenfunction for k, then psi of x is n dot x times phi of x is the eigenfunction for k star. And here is the most important steps reminding us what the relationship and the definition of the inner product and the definition of the weight function is any constant times n dot x. And here is the reminder of the relationship for the benchmark. Okay, so just as I said, applications and future work. This is not work that is supported by anyone. So my research is actually supported on the translational side for things that society considers much more useful. But I still spend a part of my time, and all the students who are now helping me with this is not part of their thesis, but this is just volunteer work. It's completely optional for them. If they don't want to do this, I can just continue to do it on my own. But many of them are curious and they want to participate. So some of the future papers will have co-authors because the students are also volunteering their time. So I want to do a bioorthogonal representation. For example, if you have a point force outside an ellipsoid, that is an unsolved problem. But I believe we can now come out with new velocity strategies using bioorthogonal expansion and the eigenfunction expansion to calculate and extend the classical solution of Ozane for a point force outside an ellipsoid. And of course, for those interested in numerical analysis and calculation, the eigenfunction relationship, that special relationship that I want on my tombstone, actually produces a very nice estimate for integrals involving the surface of an ellipsoid. And of course, that's a surface with 3 different radii of curvature. So if you want to do differential geometry and have results for nearly singular integrals, you get new integral identities from the ellipsoid at different points on the ellipsoidal surface, which actually provide very useful estimates to help for singularity subtraction methods, for example, in boundary element calculations. So people doing numerical analysis will also find some of these equations very useful. So I know this is not the same as my talk on Thursday, but I wanted to share with you some of my own research that I still do in fluid mechanics. It is very mathematical. I do not need a lab. I just need pen and paper. I don't even need a computer. But this is something I still do because I think that is one of the roles of the university, is to create deeper understanding of basic knowledge and also to create new knowledge and new insights. So, thank you very much.
Thank you very much for your nice presentation. Damos un espacio para preguntas.
Oh, I also want to say that some of you are not working in fluid mechanics, or many of you are not working in fluid mechanics, and maybe I skip a lot of steps, and some of the equations I did not explain because it is a very specialized talk. I want to assure you on Thursday, my talk has no equations. Yes?
I got a question.
Yes.
First one is, this theory, can theory be extended to a population of ellipsoidal shaped particles?
Yeah, that's a very good question. So if you do multi-particle interaction, which is of course a very practical extension, it turns out when you have, for example, a dense suspension, then a single particle analysis is not very useful. However, if you have a dilute suspension and you just want to look at the first interaction, using things called the method of reflections, asymptotic methods, to look at the disturbance produced by one particle, and what it does to the second particle, and then interact back and forth. That type of analysis is greatly facilitated by this type of velocity representation because it is Cartesian, and so you can have Cartesian coordinates in the laboratory, as well as Cartesian coordinates embedded in each ellipsoid, each of which is tilted differently. And because the general expression is in Cartesian coordinates, it is easier to translate from one to the other. Whereas, of course, if you use ellipsoidal, or in the case of spheres, you use spherical coordinates, each one has its own. And to translate ellipsoidal and spherical coordinates from one particle to the one for the other particle is very complicated and not very practical. And so these expressions are actually designed for studying particle-particle interactions. And in fact, the reason why I want to do the Green's function is for a particle that's far away, its initial disturbance is like a point force. So if you can solve the point force problem, you can actually derive new integral representations to solve two-body problems of two ellipsoids and so on.
Okay. And another one, I understand that you can use this theory for maybe suspensions or medical applications, but you can use this approach for modeling, I don't know, about bubble racing in a fluid bed. So.
No, so it turns out this is all for rigid particles. So if you want to solve not just bubbles, but viscous drop that happen to be ellipsoidal in shape, these velocity representations are actually very useful because once you have the eigenfunctions, it's a velocity representation. So it's like using Lamb's general solution for a sphere. These solutions are designed to play the same role as Lamb's general solution does for a sphere. So if you want to solve for the motion of a single viscous drop, both outside and inside, and happen to be instantaneously ellipsoidal in shape, part of this goal of finding all these velocity representations is to find simple solutions for the velocities inside the viscous drop and outside the viscous drop.
Yeah.
So these are all things I want to work on.
Thank you very much.
Good morning. The question is, why is so complicated applying wave functions for a particle that is confined between walls?
Particle that is
confined between two walls.
Oh, yes, yes. Extension to particles between two walls. Yes. So classically, the motion of a sphere between two walls, or motion of a sphere in a cylinder, all of those problems have been solved. But for an ellipsoid, those problems have really historically not been solved except computationally. Now it turns out if you actually want to solve that problem because it's an important result in your research, then the best way to approach them is not by these, especially if the walls are nearby. What you want to do is take the classical solution for a point force and distribute those point force multiplied by the tractions on the surface of the ellipsoid, unknown tractions, and solve the integral equation with the Green's function for the Green's function between two parallel plates or inside a cylinder and so on, and then solve that integral equation numerically. So that would be the most computationally efficient way to solve that problem. So this approach is really designed for ellipsoids in unbounded flow.
Other question?
Thank you so much, Professor Kim, for your lecture. It's really interesting. My question is specifically about your research, but about what you think of that kind of research.
Yes.
In the current age of computers, numerical methods and figure analysis is well established, and sometimes one might think that what kind of contribution could be an analytical analysis and development of equation, and sometimes I just have some ideas, but I'm not sure if to develop it.
So for the specialists in microaerodynamics and viscous flows, there is a historical reason why the surface traction is an important quantity in other applications on models. And it has to do with the Lorentz reciprocal theorem. So it turns out, whether you look at electrokinetic phenomena or the first onset elastic stresses in non-Newtonian fluids like second order fluids, or even the first inertial corrections like the Ozane correction to Stokes flow, in all of these solutions, you can do a perturbation solution for the first onset from non-ideal behavior. And those first perturbations, there is a shortcut which is published in the literature, mostly in Journal of Fluid Mechanics, that say that you can use the Faxane laws to calculate this perturbation. And the one form of the Faxane law is to use the surface traction from the zeroth order problem, which is the Stokes solution, on the surface of the particle. So now, all of those classical literature we can extend to flow past an ellipsoid because we have such a simple expression for the surface traction. And so there is a reason actually why the surface traction is worth analyzing to see if such a simple result exists. But the broader philosophical question, so if you want to think about a career in fluid mechanics, of course a career is many, many years, and one cannot have their entire career solving one very specific thing that happens to be almost like a miracle, because that may be good for one paper or 1 year, and unless you're doing other things to keep your colleagues and your university happy, you cannot spend your entire career doing, for example, what I showed you today. In fact, in my own career, I do many other things, and this was always one of the things I had in my drawer. Anytime I'm bored, I take it out and continue working on it and so on. But I think in terms of areas of interest, obviously the role of computational solution to analyze complex fluids, flows that are relevant for biomedical applications, biomedical devices, suspensions, materials processing, all of these involve microstructure complex fluids that are very much still an area of active research. So the combined understanding of fundamentals and theory, but also modern computational methods for solving complex fluids is still today, in collaboration with experimentalists, a very good area for research and for a career.
¿Alguna otra pregunta? Thank you so much for your presentation. Very nice.
Thank you.